Okay, so let's talk about the derivative. The derivative, it turns out, is something that you already know because we just talked about it in the previous section. We just weren't calling it the derivative, right? So what we were calling it in the previous section was the instantaneous rate of change, or in other words, the slope of the tangent line. So, and this was the formula for that, right? It was the limit as h approaches 0 of f of x naught plus h minus f of x naught over h. Well, that's just the derivative, and so that's what we're going to call it now. So the derivative function, well, we do kind of change our perspective a little bit, because whereas this is interested really in what the instantaneous rate of change is at a particular point, the derivative function is just an entire function that tells you what the derivative is going to be at any given arbitrary value of x, right? Anyway, but the derivative function of f with respect to x, we denote it this way with a little f apostrophe. We read that f prime, right? So f prime of x is this same thing, the same difference quotient that we've been looking at before, right? So this limit as h approaches 0 of f of x plus h minus f of x over h. So we've actually already done a couple of examples where we've calculated some derivatives. We were just calling it instantaneous rate of change, but let me give you a couple more. So let's calculate the derivative. By the way, derivative. So by the way, another way to say calculate the derivative is to say differentiate. A lot of times students and even instructors, and I might make this mistake from time to time as well, they might use the verb derive. So they might say derive this function. What they really mean is differentiate the function, right? Derive means something else. Derive means to sort of come up with the function, right? Differentiate means find the derivative of the function. So anyway, the verb is differentiate. Anyway, so let's differentiate some functions. Let's do this for f of x equals x cubed minus x. Okay, so here we go. F prime of x is going to be limit as h approaches 0 of f of x plus h minus f of x over h. So that's limit as h approaches 0, f of x plus h. That means that I'm going to look at f of x, and everywhere I see an x, I'm going to replace it with x plus h, right? So in this case, that's going to be x plus h cubed minus x plus h, right? So there's f of x plus h. And then minus f of x, right? So f of x is just the function itself, x cubed minus x, right? And then all over h, right? So this is f of x plus h. This is f of x. Right, so we've got f of x plus h minus f of x over h. Now, if you're thinking x plus h cubed is just x cubed plus h cubed, right? If you're thinking I can distribute that exponent across this addition, you're wrong. Actually, that has a special name. It's called the freshman dream. But you can't distribute exponents across addition. You can distribute exponents across multiplication and division, but not addition and subtraction. Okay, so to figure out what x plus h cubed is, you actually have to write this out and FOIL it out. So let's do that. I'm actually going to do, here's how I'm going to do it. So I know just from past experience that Pascal's triangle will give me the coefficients of this expansion. The third row of Pascal's triangle will do the trick. Actually, no, that's not true. It's the fourth row. The fourth row of Pascal's triangle is 1, 3, 3, 1. So I know that this looks like x cubed plus 3x squared h plus 3xh squared plus h cubed. right? That's what x plus h cubed will look like when you expand it. Now, if you don't know Pascal's triangle, like you don't know this rule or whatever, that's fine. Just write this out. You know, you'll have to write it out: x plus h times x plus h times x plus h. And you do a little scratch work, right? You know that this is going to be x squared plus hx plus h, so plus 2hx, right, plus h squared. And then you need to multiply that by x plus h again, so you distribute that again, right? But you should end up here when all is said and done. Okay. Anyway, so there's x plus h cubed minus x plus h. So that's minus x minus h. Then minus x cubed minus x. So that's minus x cubed plus x. Okay. All divided by h. Okay. Some stuff should be canceling, I think. I've got that and that will cancel. An x cubed and a negative x cubed will cancel. And then notice that everything else that I have left over has an h in it. So I'm going to go ahead and factor that h out. I'll be left with 3x squared plus 3xh plus h squared minus 1 all over h. And the reason it's nice to be able to factor out that h is that now the h's will cancel, right? We've got 3x squared plus 3xh plus h squared minus 1. We can go ahead and plug in h now because we're not going to, or sorry, we can go ahead and plug in 0 for h now because we're not going to get a 0 in the denominator, right? So what do we get? This goes to 0, this goes to 0. We get 3x squared minus 1. Okay, now some of you have had calculus before, or maybe you took a pre-calculus class where you learned a little bit of like differentiation rules and stuff like that, and you know the power rule, and you're thinking, well, I already know I can just take the 3 down in front and make it a 2 and blah blah blah. We're going to get to that in the next section, okay? But for now, this is how I want you to differentiate. Okay, I want you to get used to using this rule. And on a test or a quiz, if I said, you know, use the limit definition of derivatives to calculate this derivative, then this is what I want you to do. Okay, so so practice doing this. Don't move on and use like power rule and quotient rule and all of this stuff that we haven't talked about yet. We will get to it. Okay, but for now, you've got to do it the long way. Okay. So that's that one. Let me give you one more. So let's do f of x equals square root x plus 1. Let's calculate the derivative of that thing. Okay, so f prime of x is going to be limit as h approaches 0 of f of x plus h minus f of x over h. So that's limit as h approaches 0 of the square root of x plus h plus 1, right, that's f of x plus h, minus f of x, which is the square root of x plus 1, divided by h. And I think we did one very similar to this in the previous section, right? But the trick is multiply by the conjugate. Okay. And the nice thing about multiplying by the conjugate is that all of the radicals will disappear in the numerator, right? These things will, the radicals will cancel and just leave us with x plus h plus 1. The outer and inners will cancel each other because they're the same thing except with different signs. And then the lasts, the radicals will cancel and leave us with a negative x plus 1. As for the denominator, I'm not going to distribute that h because I'm hoping that I'll be able to cancel it off here pretty soon. Okay, so let's see. That x is going to cancel that. That 1 is going to cancel that 1, right? Because it's positive 1 minus a 1, right? Positive 1 minus 1. So I think what I'm left with is h over h times blah, right? Now the h's will cancel. And now if I plug in 0 for h, I get 1 over square root x plus 1 plus square root x plus 1. And that's just 1 over 2 times the square root of x plus 1. So there's that. There's that one. Okay, so that's how we calculate derivatives. Here's another example. Okay, so suppose that the position function of a particle is s of t equals 1 over t plus 1. Right, so suppose that this is the position function for some particle, okay, moving in some kind of rectilinear motion. Okay, let's find its velocity function. Okay, let's find its velocity function. Okay, well, remember the velocity is just the derivative of the position. I mean, we didn't actually say it like that in the previous section. I think what we said is the instantaneous rate of change of the position function is the same thing as its velocity, right? So using the terminology that we are introducing in this section, instantaneous rate of change is just the derivative, right? So the derivative of this position function is going to be its velocity function. So the velocity function v of t is just the derivative of the position function, right? V of t is just s prime of t. Okay, and that's going to be limit as h approaches 0 of s of t plus h minus s of t divided by h. In other words, limit as h approaches 0 of s of t plus h. So everywhere I see a t, I'm going to replace it with t plus h. So I'm going to get 1 over t plus h plus 1. So there's s of t plus h minus s of t. That's just 1 over t plus 1. And then over h. Now, the trick with these ones, whenever you've got like a rational expression, the trick is to rewrite the numerator as a single rational expression. So in order to do that, I need a common denominator, and the common denominator is going to be t plus h plus 1 times t plus 1. So this one I'm going to multiply by t plus 1 over t plus 1. And this one I'm going to multiply by t plus h plus 1 over t plus h plus 1. And notice that now I'll have matching denominators. I'm not going to distribute the stuff in the denominators. I'm just going to worry about the numerators. So this is limit, whoops, didn't mean to switch colors. Limit as h approaches 0 of t plus 1 over t plus 1 times t plus h plus 1 minus t plus h plus 1 over t plus 1 times t plus h plus 1 all over h. So now, when I do the subtraction, I have t minus t, so those will cancel. And I have 1 minus 1, so those will cancel. I'll just be left with a negative h in the numerator. Okay, and then remember, this is the same as you flip and multiply, so this h will cancel that one. We've got 1 over t plus 1 times t plus h plus 1. As h goes to 0, this factor will just go to t plus 1. So we get 1 over t plus 1 squared. Right? So there's the velocity function, right? That's the velocity function. So if you know that the position function is 1 over t plus 1, then you know that the velocity function is 1 over t plus 1 squared. Negative. I missed the negative sign there. I apologize. Anyway, but there you go. Okay. So on this particular problem, if we wanted to know like how fast is the particle moving at t equals half a second, well, so then we would just plug in 1/2 for t down here, right? And that would give us the velocity that it's moving at half a second. Okay. So we've seen several examples of differentiating, finding a derivative, right? Let me give you a few more definitions about this concept. So here's a big long definition that describes differentiability, right? So a function is differentiable at a point x naught if the limit, if this limit exists, okay? This limit doesn't always exist, and we'll see, I'll give you an example here in a second where the limit doesn't exist, but if this limit exists at x naught, then the function is differentiable at x naught. Now, if f is differentiable at every point within some interval a to b, then we say that f is differentiable on that interval a, b. If f is differentiable on negative infinity to positive infinity, then we say f is differentiable everywhere. Okay? And then there are some other loose ends about, like, well, this is an open interval, right? It's open on both ends. If you were closed on one end or maybe closed on both ends, could we talk about differentiability on, you know, a closed interval or a half closed interval? And then the answer is yes. We can define differentiability on those kinds of intervals as well. I don't think it's hugely important. It's just kind of a minor detail, and you can read in your book. Let me see if I can find the page number. You can read all about it on page 95. Bottom of page 95. If you want those details, but you know, I don't think it's hugely important to stress kind of that nitty-gritty stuff. But anyway, so this is what it means for a function to be differentiable. Basically, if its derivative exists at x naught, then it's differentiable at x naught. And if its derivative exists everywhere within a certain interval, then it's differentiable on that interval. Now, that leads us to consider the following. What is the relationship between differentiable functions and continuous functions? And this theorem gives it to us. I'm just using the same numbers as your book so that you know what to refer back to. But anyway, so this theorem tells us the relationship between differentiable functions and continuous functions, and here it is, right? Every differentiable function is continuous. Okay? So in other words, if a function is differentiable at x naught, then f is continuous at x naught. Okay? And here's a proof. The proof is pretty short. Okay? So we're given that f is differentiable at x naught. So since f is differentiable at x naught, this limit exists. Okay? Now, we want to show that f is continuous at x naught. So, in other words, we need to show that the limit is equal to the function value, right? So we need to show that limit as x approaches x naught of f of x is equal to f of x naught, right? We need to show that the limit equals the function values. Well, we could rearrange this a little bit. If we move this over to the other side, f of x naught is just a constant value, okay? So it's just a number. So we can move this over to the other side, and then we can take the limit as x approaches x naught of that thing. Since it's a constant value, it's not going to change, right? So what we end up with is this statement here, right? Limit as x approaches x naught of f of x minus f of x naught equals 0. This is what we need to show. Well, if we make the replacement x minus x naught equals h, then we get this limit, which is the same thing as this one, right? So in other words, we need to show that limit as h approaches 0 of f of x naught plus h minus f of x naught equals 0. And you'll notice that that's really similar to what the derivative is, right? So notice that limit as h approaches 0 of this thing, well, we can multiply by h over h. Okay, that doesn't change anything because we're really just multiplying by 1. And now we can take this piece, that's just the derivative, which we know exists. And then we can take this other piece, which is just limit as h approaches 0 of h. Well, this limit exists, it's the derivative, f prime of x naught. This limit exists, right? Limit as h approaches 0 of h is just 0. And then this number times 0 is going to be 0, which is exactly what we were trying to show. So there you go, right? So if f is differentiable at x naught, then it's continuous at x naught. The logic does not work the other way around, right? So this logic, it only flows in one direction. Okay, so loosely speaking, a continuous function at x naught can fail to be differentiable at x naught in two ways, right? So in other words, you can have a function that's continuous but not differentiable. Okay, so every differentiable function is continuous, but not every continuous function is differentiable. Okay, so you can have a continuous function that's not differentiable, and that can happen in two ways. So one of the ways that it could happen is if you have a corner point. A corner point is something like this. It's like this sharp, I guess, corner, right, in your graph. If you have any of those, then f is not differentiable at that point. It's continuous, right? The function's continuous there, but it's not differentiable there. Okay, so that's one way that you could have a function that's continuous but not differentiable. Another way you could have a function that's continuous but not differentiable is if you have some point that serves as a vertical, a point of vertical tangency, right? So like this point right here, right? So the function would not, this function would not be differentiable at x naught. Okay. So every differentiable function is continuous, but not every continuous function is differentiable, right? The logic only flows in one direction. So let me give you an example. So let's look at the function f of x equals absolute value of x, right? Pretty simple function. But if you think about the graph of that function, right, it looks something like this, right? It's a V shape. It's definitely got a corner point. Right? It's got a corner point right at 0. And so, according to the previous theorem, or did we call it a theorem? I can't remember. No, we didn't call it a theorem. But loosely speaking, we know that since it has a corner point, it's not differentiable at 0. So let's prove that. So part A, prove that f is not differentiable at x equals 0. Okay? In order to prove that f is not differentiable at x equals 0, we need to show that the limit doesn't exist. We need to show that the derivative doesn't exist, right? So we need to show that this limit as h approaches 0 of f of x plus h minus f of x over h. We need to show that that limit doesn't exist. So let's do it. So we need to show that limit doesn't exist. So what I'm going to do is use the piecewise definition, I think. Or actually, I just want to show that it doesn't exist at 0, not that it doesn't exist anywhere. So really I'm going to replace the x's with zeros. That way I can avoid having to use the piecewise definition for now. Because notice now, this simplifies quite a bit. 0 plus h is just h. So this is absolute value of h, and then absolute value of 0 is 0. So in other words, right, it's the limit as h approaches 0 of absolute value of h over h. Okay. Well, so if you think about absolute value of h, right, it's h if x is positive, and negative h if x is negative, right? So there's the piecewise definition of absolute value. So so let's say that x is greater than or equal to 0. Or maybe we can think of it like this, right? So absolute value of h divided by h is going to be h over h if x is greater than or equal to 0, or negative h over h if x is less than 0. So in other words, that's a positive 1 if x is bigger than or equal to 0, and a negative 1 if x is less than 0. So if you're thinking about, well, what's the limit as x approaches 0? Well, so note that the limit as h approaches 0 from the right, okay, from the right, I'd be big, x, I meant to say h, I'm sorry. Okay, so notice that if we're approaching 0 from the right, then h is positive, and so from the right we're approaching 1. But as we approach from the left, as we approach 0 from the left, this thing is going to negative 1. So since your one-sided limits don't match, that means your two-sided limits don't exist, right? So since right? So since your one-sided limits don't match, your two-sided limit does not exist. Since that limit doesn't exist, that means this limit doesn't exist, which means that f is not differentiable at 0. So we've done it, right? We've shown it. Okay, so that's part A. Now, so f is not differentiable at 0, but it's differentiable everywhere else, right? 0 is the only corner point, so 0 is the only problem. So the derivative of f still exists everywhere else, right? It still exists everywhere else. So for part B, let's find a formula for f prime of x. And actually most of the work is already done for us, right? So find a formula for f prime of x. Well, we already know that if x is less than 0, if x is less than 0, right, then the slope of this line is negative 1. If x is greater than 0, then the slope of that line is positive 1. So, and you can also see that from the work we did over here, right? So f prime of x is 1 if x is strictly greater than 0, and negative 1 if x is strictly less than 0. It's not defined when x equals 0, right? So so I didn't use I didn't put a little equals to sign here on purpose, because the derivative is not defined when x equals 0. But everywhere else the function or the derivative is defined, and this is it. Okay, so that's the derivative. That's differentiability. I just wanted to point out that there are a whole bunch of different notations for the derivative. We've been using this one, f prime of x. Another notation that you could use is this notation, d dx of f of x. Or sometimes people write that with a capital D and then x as a subscript, so they write d sub x of f of x. But another really common one is dy dx. I would say these two, f prime of x and dy dx, are probably the two most common notations that are used. D dx is used a little bit less commonly, and this one is used even less commonly than that. Y prime of x could also be used sometimes instead of f prime of x, right? But that, is pretty clear that it means the same thing. If we want to evaluate a derivative at a particular value, like say we wanted to evaluate the derivative at x equals 7, then each of these different notations has a slightly different way of expressing that, right? So if you were using the f prime notation, but you wanted to evaluate the derivative at 7 itself, you would just call that f prime of 7, right? If you were using this notation, you would call it d dx of f of x evaluated at, that's what this big vertical bar means, evaluated at x equals 7, right? You wouldn't just plug the 7 in for x there, because as we'll see in the next section, well, if you plug in 7 to the original function, then you're just going to get a number. And as we'll see in the next section, the derivative of a number is always just 0, okay? So you don't plug the 7 in there. That doesn't capture the meaning of what it is that you're trying to do. You want to take the derivative of the function first and then evaluate it at 7, right? So that's why you have to write it this way. Same way for these other notations, okay? And then this one is more like the first one. Another thing that you might see is that when you're dealing with this difference quotient here, the h is sometimes written as a delta x. And I'm not exactly sure why we use delta to mean change, but we usually think of this symbol, delta x, as the change in x. So instead of like limit as h approaches 0, you might have limit as delta x approaches 0, right? Something like that. And a delta x instead of the h is here as well. And similarly, the change in y, which you can think of the numerator as the change in y, that whole thing could just be replaced with a delta y, right? So that sometimes people write this as like limit as delta x approaches 0 of delta y over delta x, which is a really nice short way of kind of expressing the idea. But when it comes to actually performing the calculation, you end up having to unpack this here anyway. So I don't know if it's particularly useful, except that it's a shorter way to write it down. But anyway, so just for your information, right? A whole bunch of different ways that that this concept could be notated. All right. So that's all I have to say about that for now.